Part A and B on this one, I think are pretty easy. Part C, once we kind of just play around with the notation a little bit, I think we could be pretty successful on that one too. Part D is a little bit kind of weird out there, but I'm going to kind of rework that a little bit differently than what I got going on right there. But when they tell us a function is differentiable, just in the back of our mind, we know if something's differentiable, that means it's automatically continuous, right? And it tells us a couple of y values here. This means like when g of 2 is 4 and h of 2 is equal to 4. So that means when x is equal to 2, the y value is equal to 4. Gives us the equation of the tangent line. There's the slope of the tangent line. There's the 2/3 right there. All right, so then when it says find h prime of 2, you know h prime of 2 is just the slope of the tangent line. And this is the tangent line to both the g graph and the h graph. So whatever the slope of that tangent line is, that's what the derivative is. So that slope is simply equal to 2/3, and a is done. Part B says we got this accelerator, so not accelerator, just a equals this, right? Write an expression for the derivative and then do a prime of 2. So this is a product and you're supposed to do a derivative of that. So you're just going to do the product rule, right? So the 3, you could leave that as part of the first function. I just pulled it out in front of everything. And then I did a product rule just with the x cubed as my first function and the h of x as my second function. So I did first times the derivative of the second plus the second times the derivative of the first. And then it said, so there's the expression for a prime of x. So they did want that as your first part of your answer right there. And then it says to evaluate a prime of 2, which means you take the 2, plug it in for all the x's, and then so 2 cubed was 8. H prime of 2 is what we found in part A, which was the 2/3. And then h of 2, all right, we're going to come back to that. And then when I plug in the 2 there, 2 squared is 4 times 3, which is 12. And then h of 2, it gives us up here that the h of 2 is equal to 4, right? And then so I just do some basic arithmetic there. You can do some old school multiplication because we didn't have a calculator on this problem. And then A and B are done. All right, now letter C starts to look a little tricky. And they're really kind of hammering home this like formal definition of continuity, which is on our blue package right there. And I'm going to share with you a couple parts of this you can kind of get without the technicalities and stuff there, right? So it gives us this H function. And then it says that the limit can be evaluated using L'Hopital's rule. Now, if it can be evaluated in L'Hopital's rule, that means this is going to be like a 0 over 0 or infinity over infinity. But if you're doing limit as x approaches 2, you know when you plug in the 2 for the top part, you're going to get 0 on the top, which means if they're saying we can use L'Hopital's rule, that means the bottom part is automatically going to have to be equal to 0 as well. So before I even read anything else, if that bottom part has to be 0, I know that that f of x, that part has to be a 1 right there. So I go 1 minus 1 cubed, and I have 0 over 0, and then L'Hopital's rule can be applied. So there's that, all right? But you have this limit problem, and it says use the limit to find f of 2 and f prime of 2, and then show the work that leads to your answers there. So this particular part, letter C, was worth 4 points there. I'm going to highlight each of the 4 things that you need to have to get your 4 points. Now, when it says to find f of 2 is what we talked about. That part has to be equal to 1 because then you have 1 minus 1, which is equal to 0. So, I mean, if you could come up with f of 2 is equal to 1, that's going to be worth a point right there. And then if you're doing L'Hopital's rule, like doing the derivative of the top and doing the derivative of the bottom, you'll get another point. And then if you kind of connect that to that main definition of continuity, you can find that derivative, you'll get another point right there. So let's just kind of start this thing over here, okay? So I'm supposed to do a limit as x approaches 2 of h of x. There's my h of x. So I'm just going to plug that in right there. I want to find the limit as x approaches 2 of that. Now, here's the thing. So since it told us at the top, the h function is differentiable. If something's differentiable, that means it's automatically continuous. So I just jotted down h is continuous and differentiable. That means we're allowed to use L'Hopital's rule and everything is just kind of nice and it works, all right? Now, if you have a continuous function, let's kind of review this formal definition of continuity because this has been on there a little bit more recently, okay? One of the focus points. The main definition of continuity that boils down to this third part there. This is what we did way back in chapter 1. You have to have a y value, you have to have a limit, and then to be continuous, which means you're not going to lift up your pencil when you're drawing that curve. The limit must be equal to the y value. So the limit has to be equal to the y value. Now, if we know a function is continuous, that means we know the limit is equal to the y value. So that means I wrote down right away, since I have a continuous function, the limit as x approaches 2 is equal to h of 2. Okay, so that's our matching right there. At x equals 2, the limit is equal to the y value. And then so the h of x, again, I just took that h of x, plug that in right there. So I have the limit as x approaches 2, and then h of 2, we know that that is equal to 4. So if you just have this part written down, like that limit is equal to the y value, that's worth a point. And then knowing that L'Hopital's rule is going to work here, when you plug in 2 to the top, you're going to get 0, which means if L'Hopital's rule is applying, the bottom limit is also equal to 0. So this bottom piece also must be equal to 0. So the only way that's going to be true is if that f of 2, when you plug that in, if that's equal to 1, because then you have 1 minus 1 cubed, which is equal to 0, and then you can use L'Hopital's rule. So if you just know that the limit is equal to the y value, and then you find that f of 2 is equal to 1, that's 2 out of the 4 points. And then you all know, even if you had trouble connecting that with the 4 somehow, you know how to do L'Hopital's rule. And if you're just using the L'Hopital's rule and doing those derivatives correctly, you're going to get another point there, right? So let's apply L'Hopital's rule here. I'm going to do my limit as x approaches 2. It's important to have that notation in there still. Do a limit of the top, the derivative of the top, which is a simple 2x, and then the derivative of the bottom. The derivative of the 1 is 0. So that negative is there. So you're going to, and this is something raised to a power. So we're going to multiply by the power to get a -3. Leave the inside alone, decrease the power by 1, times it by the derivative of the inside. And again, that's the L'Hopital's rule. So I just did the derivative of the top and the bottom, and that limit answer is still what you're trying to find when you do L'Hopital's rule. So we know that limit answer is still equivalent to 4. And now when you take the 2 and plug it in for the x's now, you got the 4 there, and then you get this f of 2, which we said was equal to 1. And then that's just -3. So you get -4/3, and then the f prime of 2 is on the bottom, and then that's what we're trying to figure out. And so you just solve that equation. I multiply both sides by that 3f prime of 2 to get a 12f prime of 2, divided both sides by the 12, and I got that -1/3 there. So 1 point for limit is the y value, 1 point for that, 1 point for doing your derivatives like your L'Hopital's rule, and another point just for that right there. But I thought that's kind of like the first time we're kind of seeing all that. We had something in the past with the formal definition continuity, but that's a little more, I thought it was a little more involved there. So that's just a good problem for us to see and get exposed to and kind of study with that stuff. Now, there's my work for letter D. I'm going to talk through that, but I'm also going to talk through this a little bit quickly. Letter D was only worth like 1 point, just for saying is it continuous or not, with some sort of justification right there. And so here's how I would really do this thing. I was trying to be a little technical when I was writing this down here, but when they give us g of x, all right, so it just says we got a function here. It says g is smaller than h. It says k is a function satisfying that k is in between g and h. All right, that's all we're saying there. It wants to know is k continuous. Now, it tells us up top that the g and h are differentiable. So I know that g and h are continuous. So you're putting a function in between 2 continuous functions. That's what's going on here, okay? So I think when I first worked out, I thought that was just an odd problem. To me, it's kind of a stupid problem there, but it's all right. If you start with this, and it's only worth a point there, so as long as you just, get it right, and then it just says is it continuous or not, so, take a crack at it, right? But it says that x equals 2. So one thing that we could do is just plug in 2 for all the x's. So we'll go g of 2 is less than or equal to k of 2, is less than or equal to h of 2. And then up here, it tells us that g of 2 and h of 2 are both equal to 4. So if I put a 4 there and a 4 there, and I don't know what k of 2 is equal to, well, heck, I mean, it says k of 2 is now sandwiched in between 4 and 4. So if you're in between 4 and 4, that means the k of 2 is equal to 4, okay? Which means that's your y value, okay? That's your y value. Now remember your continuity definition. Continuous is it's going to be continuous as if the limit is equal to that y value. Now, one of the things we did this a long time ago, if you go back up to this part here, and what you can do is just do the limit of all 3 parts. So you could do limit as x approaches 2 of the g of x, limit as x approaches 2 of the k of x, limit as x approaches 2 of the h of x, right? And so now the limits are in between there. Now the limit as x approaches 2, since g and h are continuous functions, the limits are equal to the y value. So the limit of that is 4. And then I have the limit as x approaches 2 of this k of x. And then again, since h of 2 is equal to 4, and it's a continuous function, the limit and the y value are equal to each other. So that's also equal to 4. So now we're saying the limit of that k of x as x approaches 2 is in between 4 and 4, which would force that limit to also be equal to 4. And then notice that this is your limit, and then notice that your limit is equal to the y value, which means that's what's going to make that k is continuous right there. So at least you're going to throw something down there, you know, continuous or not continuous, but you know, you got to try to make that connection between the limit and that y value. And that's all I got going on down right here. So at first I did the limit part first and said, okay, the limit, it has to be equal to 4. And then I was just plugging in the 2's, and then that means the y value is 4. So since that limit is equal to the y value, that's going to be a continuous function there. So try to focus in, make sure A and B are easy for you. Make sure we work out letter C. If we work out letter C, we could really do some good work with that stuff there, because you guys would be okay taking that derivatives. You could just practice that a little bit. Letter D, I mean, you just, sometimes there's weird things on there like that. So you just do the best you can and just go on to the next problem there. Don't worry too much about that there. Skills.